Hello, everybody. Thank you for your interest in engineering application of AI. Today, let's spend a few minutes to look at this paper. This is a recent paper that we presented at 2022 International Pittsburgh Coal Conference. It's a virtual due to pandemic. So the title of this project and paper is dynamic simulation for boiler for detection and diagnosis using AI. So boiler is part of the steam power plant that we use to generate electrical power. So and dynamic simulation is a simulator that we uh, prepared using this modeling software called APROS. So in this work, uh, we have done a simulation using the boiler model to simulate both normal and fault scenarios. And the data was passed to machine learning experts, uh, uh, Yiwei Fu and Fred Xue from GE Research. And the modeling simulation work was done by the steam power team, the Ben Sargent, Tim Braun, Evnaya Jashi. I serve as project leader on the GE steam power side, and the Fred is actually the project leader or principal investigator for this whole project, sponsored by DOE and the GE Research. So it's good collaboration between GE Steam Power and the GE Research. So here's the abstract. You can read that when you get the paper. Look at the keywords: steam power plant, boiler, dynamic modeling, fault simulation, fault detection, diagnosis, and machine learning. So this is the whole thing, a whole picture that Fred and Yiwei uh, used in the proposal, and basically get the data, either field test data or simulation data, pre-process that, and create the multivariate time series. So you prepare the data that can feed into different types of machine learning models. The first one is deep similarity net that's used for detection. In the previous presentation, we talked about the difference between detection and diagnosis. Detection basically to tell the difference between normal and abnormal conditions. So and the diagnosis basically to do classification and the root cause analysis of faults or different faults. So this one you can use deep causal embedding network. So you can do causal analysis, for example. So that's the big picture that Fred and Iwi used on the G research proposal. And this was granted in 2019, and the whole project was collaborated with EPRI, Electrical Power Research Institute. Susan Manley and Steve Searchman were involved. Uh, Susan was my project leader when I led the project on chem looping, dynamic simulation, and advanced controls between 2007 and 2012. So, and in order to, so here we list the typical boiler faults. So this is based on the input from the boiler process experts. So this is a list of typical faults that the experts recommended. So, and this is a big list. But to do the simulation, we prepared a model. So we select a reference model at this scale, 660 megawatt, and this is the parameters for the plant, and this is the field we use. So What does model include both process? This is process diagram as the controls diagram. So this is a give example of the model including multiple diagrams, process diagram, and multiple control diagram, or what we call the automation diagram. So this is example for superheated steam temperature control. So, and this is the example for superheated process diagram. So it's got pipelines, heat exchangers, all these valves and all these things. So, and this lists what controls are included. So the model is not just steady state model, it's a dynamic model which you can simulate operation of the boiler of the power generation unit between low load and full load. So with different load ramping rate. So what we simulate is we create what we call a load profile. So we change load. We define the load at from 75 to 88 to 100 and back to 79. So with different load variations, and then giving using different ramping rate. And with this fit into the model, you get the simulation data. So yeah, outlet steam parameters and flow gas. So this is examples, and then with the same model we inject the force. Means how to inject force just to change some parameters in the simulator. For example, to simulate a CPU temperature sensor bias, means you got inaccuracy or errors plus or minus degree C Celsius, or the valve leakage at closed position, means is at a closed position but still have flow. That's the operating force of valve, and there's tube leakage. And the tube leakage can water or steam leak from the superheated tube. In this case, superheat is a steam, so water wall can have water leak into the furnace. So primary air leakage, air leakage from the L side, L pipe to the flue gas side. So the economize surface volume. Volume can cause problem for heat exchanger. The overall heat change coefficient can drop. So, and superheat the valve stuck to a certain position means the controller can keep calculating, but the signal sent to the valve as the actuator, but the actuator as it's stuck to a certain position cannot move. So this is a typical force we can encounter in real plant operation. And then this basically show how we simulate. We got a sensor and add the bias here, either plus minus, and then it generate the value like this and record it from the simulator and export it to as data file, text file. And then this is another one, simulate the valve leaking at closed positions, and you generate the data. And this one basically simulates superheated leakage. That means you got the steam leaked from the steam superheated steam into the flue gas side. So and this one shows how we simulate. Start with normal and then we inject the force. So and we collect the data for. And this one similarly, there's create a force with preheater leakage. So you get this leak into the air leak into the flue gas side. So from the outside leak into the flue gas side. So start from normal and then add force. So at T equals 30 minutes. So, and then we simulate the scenario of economizer falling. An economizer is a heat exchanger. So with falling, and the heat transfer coefficient will be reduced. So that's how it works. So same thing. Start with normal, stabilize. And then at T equals 30 minutes, we inject this forward. So And the last one is similar to the CPU display valve, the stock. Means the controller try to drive that, but the valve does not move. So all this data will be fit into a machine learning network. The machine learning network, this was done by Yiwei and Fred at G Research. And then with that, we train a model, and then we use that to detect or predict and detect different faults. And also, they create an algorithm to examine the rate of false alarm. So to make and this and for leakage at different levels, this basically can separate uh, the 40 data from the normal data. So it's a study, and all the data will have been prepared by Fred and Yiwei and published in a database of DOE, so everybody can access that and use that the standard data set for training different algorithms. So and look at this. So yeah. So this is a study. I mean, this is sponsored by DOE NATO and the G Power and G Research. So and this list actually previously my advisor Ken Pearl and the Reach is another faculty of or former faculty at Custom Reserve did similar work, but using self-organized agent-based sensor network to do for detection diagnosis. That's 2016. We from Steam Power did a similar work. I mean, but by providing simulation data, different fault simulation, but it's different method. We clarify sensor, actuator, and process force, and send the data to CAS, and CAS just using the self-organized agent-based sensor network to do fault detection diagnosis. So okay, this is the Yiwei and Fraz's paper. Um, um, I'm not on fault detection for multivariable time series, and this is published on International Joint Conference on Neural Network. So you can, yeah, I can put this in the description or comment area, so you can access and read this paper, and you can send them emails and to discuss the algorithm with them. They are the machine learning scientists you want to discuss with. So so we created a short video, and hopefully it will be useful to you all.